Alright everybody, we're going to start here by adding some water to our flask. Just enough to cover up the big bead of mercury there. I don't know if you can see it. Well, now it is mini beads. Alright, so you can see the mercury there. We've got some water in here. I'm going to turn on the stirring. Okay, there we go. I'm doing this in an Erlenmeyer boiling flask so that it will catch any aerosols that might be generated, although I'm not planning on generating any, but that's what the purpose of an Erlenmeyer flask is. That's why it's, shaped like a cone. It's meant to either catch refluxing vapors or aerosols. The better to keep anything toxic contained inside of it. So I'm going to add some 47% nitric acid. Okay. That's cool as hell. I went ahead and added in some more mercury since I used up all my concentrated nitric acid on this. I figured I might as well, get my money's worth out of it. So, what I've got here total is 24.6 grams of mercury. That will be dissolved into this nitric acid to make mercury 2 nitrate. And of course, like I said before, most of that is going to be converted into mercuric oxide for use in making other compounds. Some of it I'll keep as Tetraiodocadmate. Which one in particular I'll end up keeping it as, I'm not really sure. But I'll keep one. Still think it's pretty cool the way the mercury looks dissolving in there. It almost looks like a little bacterium. Okay everyone, so this is some of our mercury 2 nitrate that I've diluted down with some distilled water. This is a fairly concentrated solution of sodium iodide. So what should happen first when we add this in is mercury 2 iodide should precipitate out all over the place. Just like that. I do not want to slosh this crap on myself. Now, let's see. Stir ride might be helpful here. Isn't that nice? It is like a brilliant orange color, man. It's like you would imagine toxic waste to look like. Anyway, if we keep adding sodium iodide, the mercuric iodide will dissolve, and what we will be left with is a solution of sodium tetraiodomercurate. Yep, just like that. So this is sodium tetraiodomercurate. Very nice. It's a deep red color. I don't know if that's from excess iodine that's reacted with it. Maybe some iodide was converted to iodine. It kind of looked like that was happening there when I added it in a couple times. Okay. Yeah. All right. It is all dissolved. Cool. So what we're going to do now is we're going to make a few tetraiodomercurates and see what they're like. Alright everyone, minor change of plans. Before we jump into doing the different tetraiodomercurates, I want to find out if tetraiodocadmate is a thing. I'm very, very curious about this now. This is a little bit of the... I'm just going to start calling this Nessler's reagent, guys, because that's what it basically is. So it's sodium and not potassium, but same difference. And that's easier than saying tetraiodomercurate every damn time I want to mention it. So, took some of the Nessler's reagent, put it in here. I've got some silver nitrate here, so we're going to add some silver nitrate to this so that we can just get a little bit of the silver tetraiodomercurate, see? So that we have something to compare it to. Now this is a little bit of cadmium iodide that I dissolved just in plain old water. And this is the last of the sodium iodide I used in the Nessler's reagent. So it should be more than enough. Interesting, interesting. Are you staying focused, you piece of shit? Probably not. Alright. Well, let's see if it precipitates anything out with silver nitrate. Now we know this will. There we go. That's the famous thermochromic compound silver tetraiodomercurate. It's yellow when it's cold, red when it's hot, and orange when it's in between. Now, moment of truth. Well, I'll be damned. And it's even a paler yellow, just like that weird little document I found said. Okay, so the tetraiodocadmate ion is not colored, but you can precipitate them out of aqueous solution just fine. So I have no idea why that weird little publication said that you couldn't, and that it required high temperature fusion of the iodides together. That is just bizarre. I mean, this came out after the Cold War, too, so this wasn't some, like, you know, I don't even know, some kind of bizarre CIA anti-commie misinformation thing. I don't even know, man. Alright, well, okay, we've settled that question. See, when in doubt, consult the universe. She'll always tell you what's up. Damn, I'm actually going to save that and keep it, just to say I've got it. This is probably going to go in mercury recycling. And yeah, let me go ahead and tell you about that real quick. So, obviously, mercury waste, you can't just chuck it out in the trash. You can't dump it out in the woods somewhere. I mean, I guess you could. That'd be pretty, I don't know, kind of messed up, really. I mean, I don't know, eventually it would get locked up in minerals again, but it might do a lot of damage on the way, contaminate some groundwater, seep into somebody's well water. Yeah, you don't want that on your conscience. So I'm saving everything here. It's I'm using an actual good bottle because like with iodine recycling, I want to make sure all vapors stay contained in that damn thing. And I'll just keep everything in there until I figure out a way to get the mercury out of all of the different waste compounds that end up going in there. And if you guess that's a chore I'm going to put off for some time, you know me well. Oh, that's the kind of thing you research for a while to make sure you've got a nice, easy way to do it. See? And if I had waited to find a nice, easy way of, like, say, recycling ruthenium without having to worry about possibly hitting the tetroxide, which you can do just by fucking adding bleach to it and waiting for 24 hours. Sodium hypochlorite will convert ruthenium, if it's it has to be exposed to oxygen, over about 24 hours, it'll convert it all into ruthenate. And I have actually precipitated out this barium ruthenate, but it's a little weird. It doesn't look quite right, man. There's a brighter compound in it, and I don't know what the fuck that is. So I don't think it's a superior method for producing barium ruthenate. I think the way I did it in my video is probably the best way. But anyway, I don't know how I got off talking about ruthenate. Alright, everybody, so these are the solutions that I've got for us to try combining the Nessler's reagent with to see what, if anything, precipitates. We have nickel diiodide here, cadmium iodide. You are focused right, you piece of shit. Samarium iodide. Let's see how it does with a lanthanide. Rubidium iodide, to see if heavier alkali iodides will precipitate it out. And thallium iodide. Yay! There she is, the evil bitch herself. Alright. I know, right? This should be a match made in hell. So, of course, we're going to start with that one. Be very careful with this crap. Make sure you guys can see everything. I wouldn't want you to miss the action, because I sure as hell ain't doing this twice. Ooh! Oh. Alright, kind of a baby poop brown. Split pea green, maybe. Let's see if it shows up better if I do it like this. Yeah. Oh, that's a lovely color. Ah, it looks like shit. Alright, check my hands. Hands are good. Okay. I see a dribble. I'm assuming it's on the inside. Is it on the inside? Yes, on the inside. Okay. We're good. Everything's cool. Alright. Here we go. Actually, I'm going to bring this one to... Shit. Bring it down here where you guys can see it better. There's no reason to do it up there. Sorry, I'm a little preoccupied with not getting this crap on me. Rubidium. No dice. Nothing. Samarium triiodide. Nope. Not happening there. Okay, cadmium iodide. No. Darn, I would have thought it would have done that one. Okay, nickel. Are you serious? Okay, because I've read about a nickel Tetraiodocadmate. Huh. That's the damnedest thing. Okay, well, I guess not. So there you have it. It's thallium or nothing, or silver. And copper 1 Tetraiodomercurate is a thing, but I don't have any copper 1 salts. I had too much else going on to make any before I got to this part. I had also thought of testing out tetraiodozincates, but if we do that, we might just do that in a different video. Haven't done a zinc compound yet, but I don't know, those are kind of done to death. But anyway, so there we go. You guys have now seen a Tetraiodomercurate that you would never have seen anywhere else, because only I am crazy enough to make this fucking shit. Boy, that has two kinds of poisonous. It is a little beautiful when you realize just how deadly it is. I don't know why. Toxic shit is just so cool. Okay, people. Yeah, it does. I had to heat it up. It may only be coated with a surface layer of thallium tetraiodomercurate, but I mean, you can see both ways it was produced. Looks very similar to me. So that answers that question. Alright, y'all, this is the thallium tetraiodomercurate, and as you can tell, I've already been playing with it. I have been checking to see if it exhibits thermochromism, and it does. That's not too terribly dissimilar from the silver salt, except it doesn't go red. It just stays orange like this. And I think that's the best I can do without actually setting it on fire. But okay, everybody, this is the Tetraiodocadmate. As you can see, it looks very different from the Tetraiodomercurate. The solid is actually right here. Why the liquid is red, I do not know. But I checked to see if it demonstrates if it has if it's thermochromic like the Tetraiodomercurate, and it turns out that it is. Look, watch this. But interestingly, as this gets hot, it turns yellow. Look at that shit. Whereas with the Tetraiodomercurate, it's exactly the opposite. Silver Tetraiodomercurate is yellow and then turns red when you heat it up. But silver Tetraiodocadmate starts out kind of very lightly yellow colored, almost reddish in places, and then turns into a brilliant yellow when you heat it up. Look at that, isn't that fucking cool? That is gorgeous. So, there we go. We answered that question. Hello, turn off, you piece of shit. Alright, let's try that again. I have a fairly concentrated sodium hydroxide solution. We'll just try. And there we have it, people. Mercuric oxide. Now, the reason that this is different from mercury oxide you might see in other places is because the color depends on the particle size. So when you precipitate it out, I actually thought it was going to end up being yellow. Orange was not a color I was really expecting, but hey, you know, whatever. So yeah, it all has to do with the particle size, and apparently this somehow ended up being intermediate between yellow and red. Maybe it's a mixture of yellow and red. I don't know. But anyway, it kind of looks like pumpkin pie filling. That'd be one hell of a pie, right? So at this point, guys, I'm going to go ahead and end the video here. So the usual spiel, if you liked it, give it a thumbs up. If you didn't like it, give it a thumbs down. Subscribe, comment, share the video. And until the next one, y'all, I will see you later.